Well, good afternoon. It's 2:35. Sorry I'm 5 minutes late getting started, but I had a student from my last class needing to pick up a test from another student in a different class, so I had to go back to my office, get the test, and then wound up having to make a copy of it because I had already given them all out, and so either he lost his or someone else had gotten two. But anyway, all that's done, but that just ate up the entire time I had between classes, which is less than 15 minutes to start with. So anyway, let's get going today. This is a differential equation by 238. Supposed to be starting at 2:30, and I'm the only one in the room right now, so we'll get started where we left off last time. I'll wait and save announcements until I get at least a person in the class. Okay, we are in Chapter 4, Higher Order Differential Equations. 4.3 is Homogeneous and Linear Equations with Constant Coefficients. That's what we've been working at, and we had done examples 1 and 2, but then they have two equations worth knowing, they say, which is sort of a weird way of saying this, but here's a couple of equations. Well, let me get my pen set up. Okay. Y double prime plus k squared y is equal to 0. Okay? The other one is y double prime minus k squared y is equal to 0. Okay? Now, where the k's are any real numbers, these two differential equations are important in applied mathematics. And the auxiliary equation for the first one here would be m squared plus k squared, okay, is equal to 0. Now, pretty obvious there's no real roots, okay? So your m1 would be ki, positive ki. Wait, I've just been doing vectors, and I'm putting a vector symbol on top, a unit vector symbol on top. This is the I, which is the imaginary number, and m2 is minus ki. Okay, almost did it again. Okay. So in this case, your alpha is equal to 0. There is no real component, and your beta is equal to k. Okay? Now, from, on the previous page, your conjugate complex roots, the bottom, well, actually, top of this page, your general solution would be y is equal to C1. Now, with alpha being 0, there is no e to the alpha x. E to the 0x is e to the 0, which is 1. So it's C1 cosine beta x plus C2 sine beta x. That's it. Those are your solutions. Where, of course, your beta, I'm sorry, I should have put k in there. C1 cosine kx plus C2 sine kx. Okay? Now, you may have actually run into those before, but you probably didn't have to go through the imaginary roots and all that kind of stuff. You just knew that the second derivative of a sine or a cosine was going to give you the opposite of the sine or cosine, so that these worked out to do that. So those are your solutions there. On the other hand, when you have m squared minus k squared equals 0, you have two real solutions. Factor this, m plus k times m minus k equals 0. So m is equal to minus k, or m is equal to k. So then your solutions is y is equal to C1 e to the minus kx plus c2 e to the kx. Okay? All right. They put them in the opposite order. It doesn't matter. They put the positive k1 first and the minus k1 second. All right. Now, with a particular selection of your C1s and C2s, C1 and C2 both equal to 1/2, and C1 1/2 and C2 minus 1/2, you get special forms of the hyperbolic secant and hyperbolic cosecant functions. And they are linearly independent, so you can also write those solutions as, if it's any good for you, C1 cosecant, hyperbolic cosecant kx plus C2 hyperbolic sine kx. Okay. Now these make them look very, very similar, but understand, secant, sines and cosines and hyperbolic sines and hyperbolic cosines have really nothing to do with each other at all. They call them hyperbolic just because a few of their features, as in derivatives and integrations and stuff like that, are somewhat similar. And that's about it, folks. Some of their identities are somewhat similar. They're none completely similar. There's always one or two sign changes that will be showing up in weird places, but they just give them that name. In reality, the hyperbolic sine, I'll do the cosine first. Hyperbolic cosine, I'm ready to write a k, but not there. Hyperbolic cosine, and this is in your text too, is 1/2 e to the kx plus e to the minus kx. And hyperbolic sine, it was sort of dumb looking putting the parentheses up there. The hyperbolic sine, this is of kx, got to put that in there, of kx is equal to 1/2 the difference of e to the kx minus e to the minus kx. Okay, so that's how you can make that connection. And frankly, if I can avoid it, I usually avoid the hyperbolics. It's not that it's not a good form, it is perfectly good form, but it, like I said, they're similar enough but not quite the same that you have to then remember where the plus or minuses go to make them different. And in so doing, that's harder to me. If I deal with exponential functions, those are so easy to deal with, and I don't have to get them confused with sines and cosines. Okay. Now, so that took care of those two special functions at the bottom. Okay. Let's clear my screen here and hit the higher order equations at the top of page 138. In order to solve an nth order differential equation, where all the coefficients are real constants, no complex constants other than real constants, and none with any i's in them, and none that are variable constants. They're all variable coefficients. They're all real constant coefficients. And you had this, your auxiliary equation. I'm not going to write the differential equation. Thank you very much. The auxiliary equation would be a sub n m to the n, okay, make sure that, okay, plus a sub n minus 1 times m to the n minus 1 plus a sub n minus 2 times m to the n minus 2 plus dot 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 all the way down to a sub 2 m squared plus a sub 1 m plus a sub 0 equals 0. Okay, if you have an nth order linear differential equation with constant coefficients, real coefficients, then your auxiliary equation looks like this. I don't know if you remember back from algebra classes, especially pre-calculus algebra, you spent a lot of time trying to solve polynomial equations. That's a polynomial equation. Okay? You had rules such as the Cart's rule of signs. You had rules such as the rational zeros test. You had things like you had synthetic division you could use. You had the upper bound test, the lower bound test. You had all these different things that helped you figure out what those solutions would be. So the primary one being, in my mind, the Cart's rule of signs was always pretty easy to do, and then the rational zeros test. And if all these are real coefficients, actually these need to be rational coefficients for this to work, then that's what you proceed with that. Now, what you do is come up with if all the roots of this equation here are real and distinct, okay, we're not going to allow any imaginary roots, we're not going to allow any double roots and triple roots, multiple roots, real and distinct, then your solution, this is like case 1, be y is equal to c1 e to the m1 x plus c2 e to the m2x plus c3 e to the m3x plus plus c sub n. What do they count? Well, they just do n. Now let's do n minus 1 e to the m sub n minus 1 x plus c sub n e to the m sub n x. Okay. Those would be your general solution. If every one of these were real, distinct roots, then you just list them out. That was similar to your case 1 on the page 136. Okay? Now, somewhat harder to summarize cases 2 and 3 because roots of auxiliary equations of degree greater than 2 can occur in many combinations. Okay? Fifth degree equation could have 5 distinct real roots, 3 distinct real roots, and 2 complex roots, 1 real root, 4 complex roots, 5 real but equal roots, 5 real roots, but 2 of them equal. I mean, it just gets crazy. So when M1 is a root of multiplicity K of an nth degree auxiliary equation, that is, K roots are equal to M1, then it can be shown that the linearly independent solutions, and this pretty much follows from case 2, okay? If you have a multiplicity of K, then you'll have an M X, let's see what they call it, M1X, okay? And all these have the same. And the next one would be X e to the M1X. The next one would be X squared e to the M1X. And they keep going until you get to the kth one, and it'd be X to the K minus 1 e to the M1X. Okay? Now, notice here, you had K, a multiplicity of K of a root, okay? X, M sub 1 had 5 identical roots, okay, strange case, but if it was, then you need 5 of these. 1, 2, 3, 4, 5. Okay, the fifth one would be the k minus 1, because you see it was the second one that has the x to the first power, third one the x to the second power, the kth one would have x to the k minus 1 power. Okay, so every multiple root you're going to have that kind of situation. Okay, and then your general linear combination would have a C1e to the m1x plus C2x e to the m1x plus C3 x squared e to the m1x plus dot 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 all the way up to plus x to the k minus 1, whatever your k was, C sub k e to the m1x. Okay. You go up to that last one. C sub k x to the k minus 1 e to the m1x. Okay? Now, when the coefficients are real, now this is a strange statement here. When the coefficients are real, the complex roots of auxiliary equations always appear in conjugate pairs. Okay? So a cubic polynomial can have at most 2 complex roots, and they'll be complex conjugates of each other, those 2 complex roots. So if always have an even number of them, and they always occur in conjugate pairs. And then you use the same type of a deal that you did in case 3. It's not that hard to extend it. So let's do example 3. I don't remember now which one this is. Here is your differential equation. Y, the third derivative of y, plus 3y double prime. All right, good deal. All right. I waited to do the announcements until I got some living body here, okay? Not talking to an imaginary audience here. So while the projector's coming up, let me hit it. I think I've said this before, and I know you've been here every time I've been here, so you've probably heard it before. And I forgot to mark that you were the only one here. I got you marked, but I didn't mark the other absences last time. And then this time, again, you're the only one here so far. Hopefully someone else will be coming next. All right, so let me go through the analysis. First, okay, have you done student course evaluations yet?
I tried to. It seems like I tried to do that today. But not yet. No.
Yeah, okay, fine. Just be sure to do them or try to do them. And if you have difficulties, let someone know. It will. I probably can't help too much, but I can find someone who can help. Okay. Okay, and I think you got an email. Have you ever checked Lawson email?
Oh, yeah.
Okay, yeah. Check your Lawson email, and there's a link there that takes you right there. That's what other students have told me. See, I don't get student emails, so I don't know, but usually they do that. And another student in the class yesterday said, yep, the email's there. So they all went looking for it. Okay, so there's that. Next, final exam schedule that was posted. The dean sent it out, a few weeks ago. And I printed it when I saw it, but didn't pay much attention to it until sometime later. I was going to speak to someone about it or something. And I noticed it's wrong. Okay, one thing, well, there's 2 things wrong on it, but one doesn't pertain to students. They put the final starting next Monday, which they don't start next Monday. They start next Tuesday. They go Tuesday through Monday. Strange but true. Okay, we have to have so many instructional days and stuff, and that's what they did. But she put out that they started Monday through Saturday, and that was bizarre. She just didn't pay attention. And I sent her an email, but she didn't make a change. I talked with my boss, who's in between me and her, and he said, oh yeah, she realized she made it wrong, but she decided since she'd already sent it out, maybe people had already gone by that, just let instructors do whatever they wanted. If they want to give their exams for the Monday, Wednesday classes, the even hour classes Monday, they can, or if they want to have class Monday, that's what we're supposed to do, then give them their exams either Wednesday or the following Monday. So it's up to us, and they don't let us do that, but she can do that. So anyway, we are having class Monday, and that's when I'll give you your final exam, okay? And it'll cover this chapter as much as we get covered in it. Chapter 4. Okay, now. Okay, there's that. So, what is going to happen now? I don't think there'd be a problem with it. It's the ones that are not here. That's why I'm saying it, so they can hear it too. On Monday, I will be returning. Now, okay, let's start over. Monday, your research papers are due, okay? And if I receive them by Monday, you just get your score. If I receive them after Monday, I'll take them after Monday, but you'll be losing points after Monday, okay? So, but I will take them. But your test, they have to be in by Monday because I'm returning the test on Monday, and that means correct answers will be circulated out there, and I can't accept a test coming in later because I don't know if that person saw the correct answers on someone else's test. Hopefully not, but it could have happened, and that cheapens your grade and boosts their grade, you know, and they could have copied it off you, so I don't want that to happen.
Which test is due Monday?
All the tests that you have turned in so far.
I have one out.
Yeah. Yeah, I've only had 2.
Yeah, I've got one more to do.
Right. Yeah, so that's why I said this won't be affecting you, but there are some people in the class, I think. Let me check. Yes. There's 3 people who have turned in test 2, and if you're one of those, there's 2 people that haven't turned in test 1. Okay, so they have to turn in both tests by Monday. Otherwise, they get zeros, and that's going to really rock their grades. Okay, so just a warning, but I've been encouraging people to get the things in all along. Okay, so Monday, I return all the papers to you, and hopefully you turn in everything to me, and then I give you your, we have class on Monday. As far as we get, I'll give you your final. Now, I'm going to have to make up the final before class meets, so I won't know how far we get. If we don't get as far as the final, I'll tell you those are optional questions. You know, any beyond that. If we cover it all, then all of them do. Now, if anyone is graduating this term, you're not, are you? Okay. Anyone is graduating this term, I have to have yours back in by Thursday. Sorry about that. But if you're not graduating this term, the following Monday will be fine. But any time between when I give it to you and the following Monday, that'll be fine. Unless you're graduating, then it's any time between I give it to you the following Thursday. Because graduate grades have to be due in by noon on Friday. Everybody else's grades are due in on noon on the following Wednesday. Okay, so that'll give me time to get them graded, things up. Okay, so and do see the course evaluations. I'll say that again. Any questions then? Okay. Now, I was just about to do example 3 on page 138, chapter 4, higher order differential equations, 4.3, homogeneous or homogeneous linear equations with constant coefficients. And what we're doing now is no longer strictly second order, but higher order. So this is a third order differential equation. Y triple prime plus 3y double prime minus 4y is equal to 0. Okay? Now, if you want to start all the way from scratch, we can do that, or we can go straight to the auxiliary equation. It's up to you. Frankly, I usually start from scratch just to...
Yeah.
Okay.
I remember us working on the auxiliary last
Right.
Monday.
Yeah, and you're going to get the auxiliary equation starting from scratch. That's what I said. Okay, anytime you have constant coefficients for a differential equation, whatever order it is like this, you can go straight to, you can make the assumption that your solution y is equal to e to the mx. Because you see, when you take derivatives of mx, e to the mx, you get all e's to the mx's with m's, right? Okay, so let's take those derivatives. Y prime, which doesn't show up in the differential equation, but you still need to know it, would be what?
Just mx.
M into e to the mx, right?
Oh, that's right.
Chain rule. And y double prime would be
M
m squared e to the mx, and y triple prime m cubed e to the mx. And then when you plug those into the equation we have up here, we get m cubed e to the mx plus 3 m squared e to the mx minus 4, now that's just the y, e to the mx is equal to 0. And again, just a reminder, e to the mx is never 0, so you can divide that out. That gives you your auxiliary equation. M cubed plus 3m squared minus 4 equals 0. Now, an observation here. This is not a quadratic anymore, so we can't go straight to your quadratic formula or anything else. And that is going to be something very difficult to try to factor because it's a third cubic. Okay? Now, a reminder, this is a flashback way back to pre-calculus algebra. One of the first things that you can do here, and actually I'm going to precede it by one thing that's a real easy thing to do, is Descartes' rule of signs. I don't know if you remember that, but you count your sign changes. You have plus, plus, minus. There's only one sign change there. So you know you have one positive real root to that equation. You know you do. Okay, Descartes' rule of signs tells you have one positive real root. Okay, now the next thing to do is imagine this as f of m, okay, some function of m, cubic polynomial of m. Then do f of minus m. Everywhere you see an m, plug in a minus m. So that would be a minus m cubed plus 3 times a minus m squared minus 4 equals 0. Okay? When you cube a minus m, you get minus m cubed. Because minus m times minus m is plus m squared times another minus m would be a minus m cubed. Any odd power don't make it a minus sign, and even power keeps it the same. Okay, so this one would be plus 3m squared because that's an even power, so you don't change the sign of that. Okay, and then the last one's a minus 4 equals 0. Now you count the sign changes here. Well, you have 2 sign changes. So that means you have either 2, now here's where the catch comes in, or 0. Subtract 2 from it. You either have 2 or 0 negative real roots. So this hasn't really helped a lot, but believe it or not, it helps a little bit. Okay? That's negative real roots. Real. Negative real roots. The Descartes rule of signs as written gives you the positive real root. When you substitute a minus m for the m, that gives you how many negative real roots. And whatever number you got, if this was a 7th order polynomial, okay, let's hope it's not, but if you had one that was 7th order, and you got 4 positive real roots. That would be 4 or 2 or 0. Just keep subtracting 2 until you get to 0. Well, that would leave you 3 or 1 negative real roots. Okay, so you always subtract 2. So this was 1, can't subtract 2 from it, so you know you got 1 positive real root. This tells you either got 2 or no negative real roots. Now, if you have no negative real roots, and this is the third order, that means 2 of these roots are going to be complex. And then we're going to have to use our sine and cosine. Okay, we're going to have i's. Okay, so it's not much information, but it is some, and it is useful. Okay, the next thing that we use is called the rational zeros test. I don't know if you remember how that went. What a rational zero is something that's a ratio of 2 numbers. And those ratio you could do P over Q. That's what the pre-cal book calls it, so I'm going to use the same thing. Now, what is the P? The P here is all the possible factors of your constant term. All the possible factors. That would be plus or minus 1, plus or minus 2, and plus or minus 4. Okay? And your Q is all the possible factors of your leading coefficient. Well, that's only plus or minus 1. Well, when that's a plus or minus 1 in the denominator, you've got them there. So you have a possibility of 6 possible rational zeros. Okay? You know you can only have 3, and you know only 1 can be positive, and 2 or none are going to be negative. So you see, this will help you a little bit here. Now, you always going to have 1 as a possibility. 1 is so easy to check. You just take this and plug a 1 in for M. You get 1 plus 3 is 4 minus 4 is 0. There it is. 1's 1, but that's the only one you got. Forget about plus 2 and plus 4. Can't happen. That's where the Descartes rule of science comes in helpful. Okay? Found out you had 1, is 1, 2, and 4 out of the question. Okay? So, what do you do with that? Well, now we do synthetic division. So you take that 1 real root you know that's there, 1, okay, divide it into your coefficients of this polynomial. You remember this? 1, but if you're missing a term, you have to put a 0. Well, you got a cubed term, a squared term, so 3, but you're missing a linear term, so put in a 0 for that one, and then a minus 4 for that. Okay? Now, I skip a line, draw a line. That's my little rule. Here's the other thing I do before I do that. I count how many numbers I've got there. 4 has to be 1 more than your degree here. That means if you had forgot about the 0 here and you only had 3 in degree 3, oops, we're missing 1. Missing the linear term, so you put in a 0. Now, you always bring down the first one. That's pretty simple. Okay, from now on, you're only multiplying and adding, multiplying and adding. Multiply 1 by 1 is 1. Add, you get 4. 1 times 4 is 4. Add, you get 4. 1 times 4 is 4. Add, you get 0. Okay, that's what you want to have. You knew that was a root, you better get a 0 there, because that's your remainder. What you've just done, you have divided. Remember, if this is a root, if m equal 1 is a root, that means m minus 1 is a factor of that polynomial. Okay, remember when you factored, then you set them all equal to 0, and then move the 1 across there, and you get m equal 1. Okay, yeah, so that's your factor. Well, here's your other factor, only this now is a quadratic, because you only have 3 terms. X squared plus 4x plus 4. There's your other factor. Okay. So, x equal 1 is a real root, and that's your only positive real root. Your other factor is going to be m squared plus 4m plus 4. Now, guess what? That will factor. M plus 2 times m plus 2. Right? And that does give you that, right? Well, what's your solutions? m equal minus 2 or m equal minus 2. Hey, guess what? That's a double root. So we have to follow, remember our case 2 earlier on the previous page. See, there's case 1, case 2, case 3. Case 2 was when you had a multiple root. Here we got a multiple. And by the way, these are 2 negative real roots. That's all she wrote. Because you can only have 2 or 0, we got 2. Done. If we had found 1, you keep looking more negative till you got the second. Okay. Okay.
According to, show me on case 1 where it says, or case 2, excuse me.
Yeah.
Where it says that because we have -2 and -2, it's
That is a double root. It's the same number, so there's only m equal -2, but it shows up twice. So that's what we call a double root. In case 2, it says repeated real roots. When m1 equals m2, -2 equals -2. Okay, that's what it means. We necessarily obtain one exponential and then the other. Remember, we just multiply x by it. Okay. Maybe it'll come back when I do the next step. Okay? Okay, m equal 1 is a root, m equal -2 is a root, and m's equal -2 is another root. Okay? I don't know if you remember the old Bob Newhart show, some sort of dumb show, and this guy would come up and had 2 brothers. He said, I'm, whatever his name was, it's my brother something, and my other brother something. They had the same, and other brother Daryl. Exactly. Well, that's, you got one root of 1. Hey, I'm 1, and here's my other brother 2, and my other brother -2. You know, they had the same names. That's a repeated root. Okay, so that's what we're doing here. The dumb Bob Newhart show. All right. So here is your solution. Y is equal to, let's do the first one, C1 e to the m equal 1, that would just be x. These are x's, aren't they? I assume they're x's, okay? Now, your second one is with m equal -2, plus c2 e to the minus 2x, plus c3, the third one. You can't do e to the minus 2x again. That would not be linear independent. So what we do, we put an x, e to the minus 2x. And that's what they told us to do. Go back. Okay. That's what they told us to do in case 2. C1 e to the m1x plus C2 x e to the m1x. That's what you do when you have multiple roots. And if you'd have had, I was going to say 15, but let's do 5. 5 minus 2 is here. It would be a C2 e to the minus 2x plus C3x e to the minus 2x plus C4x squared e to the minus 4x plus C5x cubed e to the minus 2x. But you just keep going up one more power of x for every one that you have. So you come up, that's what we did. I did right before you came in class. We went over that. So you can read just the preview earlier. So there's our triple, our third order differential equation, 3 arbitrary constants, 3 independent functions as your linear combination of those. Okay? And you went back and you used all the good old stuff you had from precalculus algebra. You wondered why you did it then? This is why you did it then. One of the reasons. Okay.
There's an assumption also. I remember what I took.
Oh, okay. Good deal.
That was a long time ago.
Yeah. Okay. I turned back a page. Let me turn back to page 138, and let's see what they got. Y is equal to C1 e to the x plus C2 e to the minus 2x plus C3 x e to the minus 2x. Perfect. Way to go. All right, to move? Yeah. All right. Let's do example 4, which is the fourth order. linear differential equation. Goodness gracious. Name tag stop. So here we have, let's go to Leibniz notation. It's so much more fun to write. d4y over dx fourth plus 2 d2y over dx squared plus y is equal to 0. Okay? Now you want to go straight for your auxiliary equation, or you want to go the long route? Long route? Okay, yeah. So your assumption is y is equal to e to the mx. Okay? Anytime they're constant coefficients, that's what we assume. So your y prime is going to be? Okay, and your y double prime? M squared e to the mx. Okay, I can't write. Y triple prime? M cubed x e to the mx. And your y, after triple primes, they start putting them in parentheses. Fourth prime is m to the fourth. That's the power, that's a prime, okay? E to the mx. And then what would be your, if you plug these values in, your y fourth, which is what this one is. I guess I could have written this as dy dx, d2y d2x, d3y. I'm just so much easier to write primes. Okay, so this would be m fourth e to the mx, that's y fourth prime, plus 2, this is the double prime here, m squared e to the mx, and then your y is just plus e m x equals 0, because that's equal to 0. Okay? And again, because e to the mx is never 0, you can just divide them out. That leaves a 1 here, by the way. So your equation, your auxiliary equation, is m to the fourth plus 2m squared plus 1 equals 0. Now, at this point, if you can see it, we can maybe factor that. If you can't see it, we can do a substitution, and that might help. See how that might factor? No. Okay. Here's a substitution. The minimum exponent you have is 2, and all of them are multiples of 2. So let's come up with a new, name a new variable. Don't use y, x, or m. W. Okay. Let w equal m squared. Then w squared is equal to m to the fourth, right? Okay. So now we have a w squared, that's your m fourth, plus 2, m squared is w, plus 1 equals 0. Can you factor that?
Yes.
What? How?
W plus 1
squared, or times w plus 1. Okay. Equals 0. So what are your roots?
1 plus or minus.
M equal, not plus or minus,
Just 1.
minus 1. Because you set each of those equal to 0, and that's not an m, that's a w, sorry. Okay, sorry, I forgot we changed it to w. Okay, w is equal to 1, or my other brother, w is equal to minus 1. Okay, we got 2 of them, double root. Okay, but that's for w. But w is m squared, right? So I really shouldn't have done that. We should have just done this. This is m squared plus 1 times m squared plus 1 is equal to 0. And by the way, we didn't do our Descartes' rule of signs. We could have. How many sign changes you got here? 0. So there's no real positive roots, or no positive real roots, however you want to say that. And if you put a minus sign in here, that gives you minus m to the fourth is m to the fourth, plus 2 times minus m squared is m squared, plus 1 is equal to 0. You have no negative, I'm going to write it this way this time, negative real roots.
Show me how you said if we put a negative.
Okay, put a negative m in here. Negative m raised to the fourth power. That's negative m times negative m.
Oh, yeah, you're right.
Because
the odd and even.
Yeah, odd and even. If it's an even number, you don't change the sign. If it's an odd number, you do change the sign. And they're both even, so no negative real roots. Boo hiss. Okay? Now, that means you have no real roots, and we just almost can see it here. There's no way m squared plus 1 is 0. Okay? So, m squared is equal to minus 1. That means m is equal to plus or minus I. Remember, impossible. Okay? The square root of negative 1, which is I. And here, m is equal to plus or minus I. All right, we got a real pain in the neck here in that all of our roots are complex, but they're both repeated roots as well. Plus I is repeated and minus I is repeated. So we're going to have to use your trig functions, the sines and cosines, for the imaginary part, but then you're going to have to multiply x by them for the repeated parts. So this is a pain in the neck, but I mean, it's still fairly simple to do, okay? Relatively speaking, if I could find the right page to look at. Okay. So with that being the case, if you go back to your case 3, this would mean that your alpha, which is the real part, there is none. That's equal to 0. The beta, which is the real part of the complex, is plus 1, plus or minus 1. For both of them, but both of them are repeated. Okay? So if you go back to your case 3 there, you'll see what you do is y is equal to C1. I started to put E. You would have put an E. Okay? E to the alpha x. Okay? But alpha is 0. E to the 0 is 1. So you don't put anything there. Then you put cosine of beta x. Well, your beta here is plus 1. So the cosine x plus C2 sine x and you, for the beta, you just use the numerical part. You don't ever use plus or minus. Sorry. You just use the numerical part. And it's 1. Okay. But you got 2 of them. You know, you got repeated. So the next part you put in C3, x cosine x plus C4 x sine x. Okay? And trying to find it here. Oh, there it is, bottom of page 138. They usually put it in blue, and that's what I was looking for. They didn't put it in blue this time. C1 cosine x plus C2 sine x plus C3 x cosine x plus C4 x sine x. Okay? The first, well, both of these are identical, so it would be a sine and a cosine of 1 x. Your alpha part is 0 anyway. And because you have repeated roots, you put multiply by x. If we had 3 or 7 of those, then you'd have more x's, x squareds and then x cubes, as many as it took to get them all. So those are the rules for that. So you combine your singular distinct roots, your repeated roots, and your complex roots. This had repeated and complex together. If they're singular, you just have each of the whatever x. All right. So that was example 4. Now, what I was just saying, when you have more than one of them, at the top of page 139, they just list. What if you had 2k real linearly independent solutions? Okay? Then e to the alpha x, if your imaginary part was alpha plus beta x, plus or minus beta x. It's always plus or minus beta x. So we just use the beta. We don't use the plus or minus, just like we did here. So the alpha goes with the e part, e to the alpha x, cosine beta x. And if you had 2 of those, then you'd also have an x e to the alpha x, cosine beta x. Our alpha here was 0, that's why we didn't have them. If you had 3 repeated roots, imaginary roots, they would be x squared e to the alpha x, cosine beta x, and then you keep on going. And then for every one that was a cosine, you also have one that's a sine. Okay? So that's how they do. In example 4, the k was 2, so we only went, and your alpha was 0, your beta was 1. Now, they mention here the most difficult aspect of solving constant coefficient differential equations is finding the roots of auxiliary equations. Recall from pre-calculus mathematics, if M1 is equal to P over Q is a rational root, with the energy, that's what we just did. It's the rational zeros test. Okay, P is a factor of the constant term, and Q is a factor of the leading coefficient. So I bet you that's what we're going to use next. How are we doing on time? 15 minutes, good. Okay. So let's clear this and do example 5. Here's example 5. 3y triple prime plus 5y prime, no, that's double prime, I believe it is, plus 10y prime minus 4y is equal to 0. Okay? You want to guess what your auxiliary equation is, or want to go through it brute force?
I want to go through brute force, but let's try going straight to the auxiliary.
Okay.
That's going to be.
I'll lead you off with a 3.
3, cubed.
3m cubed.
E and x.
Second?
E to the mx.
Yeah, okay, you can write that in, but you're going to divide it out, right?
Oh, that's true. You're right.
So it goes just to the auxiliary equation.
So plus 5.
Plus 5.
M squared.
M squared.
Plus 10.
Plus 10. M.
Minus 4.
Minus 4 equals 0. There's your auxiliary equation. We don't count the e's as part of the auxiliary. When you divide them out, that then becomes your auxiliary equation. Okay? Now, the book didn't mention it, but I did. Let's use the Descartes rule of signs to see how many roots you got. Now, time out first. I always check and make sure I can't divide out anything. 3, 5, no, they're both prime numbers, no common factors, so it doesn't matter what the 10 and the 4 are. Nothing on divide out. So, we did that. So, Descartes' rule of sign tells us
1
positive real root. Okay? So 1 positive, I'm abbreviating like crazy, real root. Okay? Then do the second part of the Cauchy rule of sign, which is, since that's an odd number, you change the sign, minus 3m cubed. That's an even number, leave that sign the same, plus 5m squared. That's an odd number, change that sign to minus 10m, and then this is even minus 4 equals 0. Count your number of sign changes. 2 sign changes, so you either have 2 or, subtract 2, 0 negative real roots. Okay? So we know you got to have 1 positive, and you may have 2 or none negative real roots. Okay? Now the Cauchy rule of signs. It's going to be P over Q, where P is all your possible factorizations of your 4, plus or minus 1, plus or minus 2, plus or minus 4, over all your possible factors of your leading coefficient, which is plus or minus 1 and plus or minus 3. Boo hiss. We're going to have some fractions, possible fractions in there. So I like to list what they all are. Okay? So it's going to be plus or minus, when you put them over 1, you just get the numerators. Plus or minus 1, plus or minus 2, plus or minus 3, and no, there is no plus or minus 3. Plus or minus 4. Okay? And then put them over the second denominator. It's plus or minus 1/3, plus or minus 2/3, and plus or minus 4/3. Okay. Now, if you get some bigger and more hairy numbers, after a while, some of them may start repeating themselves. These didn't. So if you had, a 6 in the denominator, plus or minus 6 in the denominator, 4 over 6 is the same as 2/3. So you don't have to do that for once. So, now, only one positive will work, and maybe none of the negatives. But I, being really lazy, always start with the easiest, which is 1. Okay? Now, if 1 works, we can just add our coefficients. If that comes out to 0, we're done. Obviously, it won't work. Okay? So don't even mess with 1. We know it won't work. So that would be positive 18 minus 4. Not going to be 0. So the next easiest is minus 1. I kind of doubt if it'll work too, but let's try it. Minus 1, and then we'll do our synthetic division. What do we put inside the house? 3, 5, 10, minus 4. Okay, now skip a line, draw a line. Bring down the 3. Multiply, you get minus 3. Add, you get, say again, 2. Multiply, you get negative 2. Add, you get 8. Multiply, you get negative 8. And you add and you get negative 12. Now, normally I wouldn't even do that, but I did want to show you this. This is another test. This is called the upper bounds test. Oh, it needed to be a lower bounds test, because this is a negative number here. If you wound up with a plus, minus down here, don't look any more negative numbers. They're not going to work. Less negative numbers may work, but more numbers negative. But this doesn't. So you can go either way. You can go down to the minus 1/3 or minus 2/3, or you can go to minus 4, minus 2, and minus 4, because you don't have an alternating signs here. It's just another little test. It doesn't, it doesn't tell you anything here except you can keep going. So let's keep going, okay? Now, because I can do it, I'm going to erase, okay? You probably have to just write over, or keep writing. I know that first one's still going to just be a 3, so I'm not going to erase it. So I go for my next. Now, I like whole numbers better than fractions, so I'm going to go for plus 2. Okay? So let's start again. 2 times 3 is? add,
11,
multiply,
22,
22, add,
32,
32, multiply,
64,
64, add,
60.
obviously not 0. That's a remainder of 60, not a 0. Now, when you're doing positive numbers in here, if you get all positives down here, stop. Don't even bother with plus 4. It's going to be worse than this. But we can still do our 1/3 and our 2/3. Or our 4/3, because those are all less than 2. Okay? So we're going to keep going on that, but we're not going to do the 4. Okay? So far, plus and minus 1 are out. Plus 2 is out. Okay? And we know plus 4 is out. Okay? Because we got positives down here. Okay? So, let's try again. Okay? Now, what you want to try for next?
One-third?
You want to go to 1/3?
Probably not. But
I don't, because it's a fraction. Let's try minus 2 first.
all right,
May not work. You probably are right.
that's right.
You probably are hit it right.
If we have got negative, positive, negative, positive, then we don't want to try any more negative.
No, any more negative negatives. Less negative negatives would work okay. You know, okay. Minus 1, if minus 1 would have been alternating signs, then don't do minus 2 or minus 4. Okay? But the minus 1/3, minus 2/3, and minus 4, no, minus 4/3. If minus 1 would have given us a alternating, then minus 4/3 out too, because it's less than minus 1. See, that's the lower bound. You don't go anything further downhill. Okay? More negative. Less negative you can do. And I left that out before, yeah. Minus 4/3 is more negative than minus 1/3, but minus 1. But that didn't turn out that way, so all of them are still good. Okay?
Yeah, so let's try negative 4 then.
How about negative 2? It's easier.
Oh, all right, negative 2.
Negative 2. Okay? Multiply.
Negative 6.
Add.
1.
Negative 1.
Negative 1.
2.
12.
12.
Negative 24.
Negative 24. Negative 28. Look at that. Alternating signs. Minus here, alternating signs here. Don't go any more negatives. Minus 2 is out, but now also minus 4 is out. So both of your 4s are out. So 1/3 is going to be, you probably were right on the money there. Okay? But I did want to show you that rule. Okay. So, and because I like positive better than negative, let's try positive 1/3 first. See if it works. 1/3 times 3 is 1. Add 6. Multiply 2. Add 12. Multiply 4. Ding, ding, ding. We've got a winner. Okay, a winner. Okay. That gave you a 0, meaning that went. So guess what, team? We have a root. It's a positive root. The Cart's rule of sign says don't go any further. So you can eliminate, we got our plus 1/3. So the plus 2/3 out, plus 4/3 out. We only needed one positive. We got it. Okay? All right. Now, but as soon as you get here, okay, another thing, this says these are all positives, so don't go any higher there either. So 2/3 and 4/3 were out there too, you know. So right now we can stop. Don't do any more synthetic division. Once you get 3 down here, that's a quadratic. We can deal with that. 3x squared plus 6x plus 12 equals 0. First thing you can see you can do is divide out of 3. right? Okay. And what I really want to do is put it outside. And what do you have left? X squared plus 2x
plus
4 equals 0. Now, obviously 3 is not 0, so let's try this one. X squared plus 2x plus 4 equals 0. Do you think you can factor that?
Yep.
Okay, what would it factor as?
X plus 2. X plus 2.
That would give you
No,
x squared
right.
plus 4x plus 4.
You're right.
Yeah. That won't factor.
Yeah, no, it won't.
So then you use the good old quadratic formula. Oh yeah, we remember that, don't we? That would be x is equal to, jot it down for you, minus b plus or minus the square root of b squared minus 4ac all divided by 2a. Okay? Where a is 1, the coefficient of the squared term, b is 2, the coefficient of the linear term, and c is 4, the constant term. So plug it in. And this works even if you could factor it, but it's usually harder to do it this way. Minus 2 plus or minus the square root of 2 squared, which is 4, minus 4 times 1 times 4 over 2 times 1 is 2. And this will give you minus 2 plus or minus the square root of 4 minus 16. Now, when I get to this point, first thing I do is count my negatives. Well, we only had 1, so it's going to be, if we had 2, that's going to be a plus sign. If we had 3, that's going to be a minus sign. Now, if we had a plus here, you're guaranteed you're going to have 2 real solutions. They may be irrational, okay, if that's not a perfect square, but when this number was negative and this is larger than that, we've got complex roots. So we go to our a plus bi, okay? And this is all over 2. So let's clean that up as much as we can. Minus 2 plus or minus the square root of negative 12 over 2, which is minus 2 plus or minus. Now, can we find any perfect squares hiding in 12? 2 isn't a perfect square. 4 is. Oh, did you mean the square of 2?
Yeah, I do mine a bit different.
Okay.
But go ahead.
Okay, yeah, but 2 squared is 4, and 4 is in there. So let's factor out a 2, factor out a 2. Plus or minus 2 times the square root of, what's left? Negative 3, right? Okay, well, negative 1's also in there, so let's factor out an I, and then you have a root 3. Okay, and in your denominator you have a 2. So what we have here, the 2 will go in to wipe out both of those 2's. You have minus 1 plus or minus I root 3. I like to put it that way so I don't think the I is underneath there. Okay, now, real part is, this is your alpha is minus 1 and your beta is root 3. These are going to be your sine cosine ones. Okay? Okay. Here was a root, right here. Remember, m, I started to say m equal 1/3 or m equal 1/3, whichever. So let's write down our 3 solutions. Is it time? Okay. I'll do it real quick. I got to go. So it's y is equal to c1 e to the 1/3 x, or x over 3. That's 1. Plus c2 e to the minus x. That's your alpha x when you do the complex one. Okay. Then the beta is cosine root 3x plus c3 e to the minus x. Those are always the same because it's the same alpha sine of root 3x. So you had one positive real root, 0 negative real roots, 2 complex roots, and you get your sines and cosines from that. But they had real parts to them, so the minus 1 put it e to the minus. So let's see if that's what they got. Hopefully they do. C1 e to the x over 3, I put 1/3 x, that means the same, plus e to the minus x, yep, cosine, or they put that on the outside, C2 cosine root 3x, and then C3 sine root 3x. They factored out the e to the minus x and it's fine. And they output root 3x is 2, and I don't like doing it. Well, it's okay. All right. So, since I don't have a computer program that will do it, I'm going to skip the use of computers. And that basically gets us to the end. 4.3, homework exercises, any of the odds that are in the back, 1 through 13. Any of them 15 to 27. Any of the odds that are in the back, 29 to 35. Any of either 37 or 39 if they're in the back, 41 if it's in the back. 43 or any of the odds 43 to 47 if they're in the back. 49 to 57 if they're in the back. Usually the discussion problems are not in the back. So I think that would be it. Okay. Now, that means next time we'll start on this thing they call undetermined coefficient superposition approach. I've taught it both superposition and annihilation, and it seems like students understand superposition a little bit better because it's sort of like what we've done before. So we'll get as far as we can with that, but we'll see what happens. I'll try to have your test ready on Monday, and we'll go from there. All right. Any questions?
Nope.
I got